Hello, Physics 30s. It's Mr. Jukley again, here today to talk to you about Millikan's explanation and evidence for Einstein's photoelectric effect. This is Unit 5, Lesson 3. Let's jump right in. So, this is what we learned last time. Einstein's photoelectric equation based on physics principle 5, based on the conservation of energy. So ETI is equal to ETF. Essentially, initially, we have photon energy coming in, and we know how to calculate that photon energy. It's HF or HC over lambda. That's the actual frequency or the actual wavelength of the photon. It's coming in. Part of its energy goes to the work function. The work function, remember, is the minimum amount of energy required to dig an electron out of that metal. It's H times F naught, where F naught is the minimum frequency. So minimum frequency corresponding to minimum energy. Or we could do, and we kind of made this one up, we did HC, sorry Einstein, I'm writing over your head here, HC over lambda naught, where lambda was our maximum wavelength, again corresponding to the minimum amount of energy. Minimum energy we talked about, well, that's just for the surface electron, so it's going to be constant, and then any energy that's left over. So the photon comes in, digs the electron out, any energy that's left over goes into our kinetic energy, which before we said was 0.5 mv squared, and that's going to be our maximum speed squared. And this whole thing was assuming that the frequency of the EMR was greater than our threshold or our minimum frequency. So assuming that that photon has enough energy to dig it out in the first place. Cool, so quick little review there. That was great. I mean, Einstein won the Nobel Prize for this, which is no small feat, but he had absolutely no experimental evidence, like no experimental evidence. It was a thought experiment. It was all in his mind. Einstein had a great mind, a great imagination, but no evidence. So what we need, and this is a person we've talked about before, Robert Millikan comes in, and Robert Millikan actually verifies Einstein's photoelectric effect. So comes up with the experimental evidence to show, yes, Einstein, you were correct in this, which is pretty spectacular. So let's check out this little animation here. You can play around with it on your own if you want to, but let's check it out. I've got it going here, our photoelectric effect. I'm just going to go ahead and set that voltage to 0. There we go. So right at the bottom, this battery is not actually doing anything. That power source is not actually doing anything. And we see our photoelectric effect. So we see the UV, is it UV in this case? UV or violet light coming in, it's hitting our metal cathode, it's ejecting electrons, and the electrons are going at all kinds of different speeds. Look at that slow one right there, and a couple really fast ones moving across. The fastest ones are our surface electrons. Those are the ones that we really want to focus on. And of course, it's coming over to the anode. The electrons then are leaving the anode and going back over to the cathode, and we've got a little bit of current, and that current can be used to do work. It's a photocell. Very nice. Here's what Millikan did in a nutshell. So he had a power source, and he increased the power source. Now this side you'll see over here is negative, and this side over here is positive. So he increased the potential difference, now making this into a parallel plate apparatus. And if we know that these are electrons that are shooting across, the more negative this side gets, the less the electrons want to be over there. And as they move from the positive side to the negative side, they're starting with their maximum kinetic energy. Remember, we're focusing on those fastest ones over here. They're leaving with maximum kinetic energy and no potential energy. And then as they travel across, they slow down, slow down, slow down, slow down. The kinetic energy turns into potential energy. And what Millikan did, and you can see it here, is he adjusted this voltage. We call it back voltage because it's forcing those electrons back. He adjusted this voltage so the electrons just barely stop before they reach the opposite plate. So all of these electrons over here are just barely stopping. They're not actually attaching to that plate, and they're not actually creating any current. So what we call this, for this particular situation, this particular metal, this particular wavelength of light, our stopping voltage, so the voltage that stops all current, is 0.8. If I were to change the wavelength a bit, so now I am decreasing the wavelength, which is increasing the frequency, you'll notice that the electrons are now making it across because this EMR has higher energy. So same work function because same metal, but it's kicking out those electrons with higher kinetic energy. So I need a larger back voltage to slow them down so that they just barely stop. That might be a little bit too much actually, but they just barely stop before they reach the opposite plate. I don't know if I'm going to be able to find this one. Oh, maybe. Yeah, that looks pretty good right there actually. So again, just barely stop. Cool. So that is the big idea. We set up a parallel plate apparatus to stop the electrons as they travel from one side to the other. We start with kinetic energy over here. We end up with potential energy over here. Nice. So let's get back into it here and let's start to explain this a little bit more and look in a little bit more detail as to Millikan's thing, except I lost my file pen. Oh, back pocket. That is a good place to check. Okay, so could you predict what this graph looks like? So our photocurrent, or current in other words, versus our back voltage. So what happened when we increased our back voltage? So back voltage is that voltage that's forcing the electrons back. Well, if I had 0 back voltage, then I have lots and lots of photocurrent. I actually have my maximum photocurrent. And then as I increased it, so increase my back voltage means we decrease our photocurrent until we get to a very, very, very particular place where there is no more photocurrent, and we call that our stopping voltage. Cool, so that's the graph that Millikan discovered. Again, highlighting a couple little pieces here. So as the back voltage increases, the current decreases until we get to that stopping voltage. That's our minimum voltage for 0 current. Excellent, very nice. So what this gives us, and what Millikan discovered for us, is a new way to actually measure the kinetic energy. Before this, it was all just a thought, right? It was a great idea, but it was just an idea. Now we've got a way that we can actually measure, right, our kinetic energy. And it goes back to physics principle 5, ETI equals ETF. So originally, this electron is starting with, and if we're focusing on just the fastest ones, it's got our maximum kinetic energy. Cool. And then as it moves across the parallel plate apparatus, it slows down, slows down, slows down until it just barely doesn't even touch the other plate, just stopping the voltage. So it's changing from kinetic energy into electric potential energy. So EPE we'll call it here. Now as I go through, well, EK max, well, it's 0.5 MV squared. That's fine. That's nothing out of the ordinary. But electric potential energy is delta V times Q, right? And in particular, let me just fix this up a little bit. It's not just any voltage. That's actually our stopping voltage times Q. What Q do you think we're talking about here? Obviously an electron, right? We're dealing with electrons here. So cool. The big thing that we get out of this, like, yeah, we can use this formula here or there. We're not going to use this version very much. What we're now going to look at is, you know what, I'll switch to the next thing here because I got it written up a little bit neater anyways. EK max, if we actually wanted to measure that maximum kinetic energy, it's the charge of the electron times the stopping voltage. Very, 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 very cool. Yeah, okay. Good stuff. What unit do you think you'd have for EK max if we're dealing with Q and V stop? So remember, we could have joules or electron volts, but in this case, because we're dealing with charge and because we're dealing with volts, which are joules per unit charge, it has to be measured in joules. So it needs to be measured in joules. So do not use electron volts for this one, long story short. Cool, so let's check out a real quick example here. So we've got photons. They are 4.03 electron volts each, and they're shone on a metal. It says the minimum potential difference to prevent photocurrent is 0.707 volts. Determine the minimum frequency to emit electrons from the metal. So there's lots of definitions built into this. So first off, this one is our photon energy, and it's measured in electron volts. We just talked about if we're using voltage, we should probably switch this to joules. So let's see, I might do that right up top here. 4.03, don't quite want that yet. 4.03 electron volts. I'm going to multiply that by, let's see, I want electron volts on the bottom, I want joules on top, so electron volts cancel. 1 electron volt is 1.6 times 10 to the negative 19 joules. So when we plug in the numbers for that, we actually end up with, let's see here, 1.1312 times 10 to the power of negative, let's check the calculator, 19 joules. Cool, okay, so we've got the energy of an individual photon. It says the minimum potential difference is 0.707. So that is our minimum potential difference, which by definition is our stopping voltage. Cool. And then it says determine the minimum frequency to emit electrons from the metal. So what we're actually looking for there is F naught. So the minimum frequency required is F naught. Cool. Okay, so let's go through and let's start to organize this. This is still, it's just an Einstein photoelectric effect thing. So we're starting with ETI equals ETF. And we know that originally we've got that photon energy. So the photon comes in, part of its energy goes to dig out the electron, and then whatever's left over goes into kinetic energy. And again, if we're talking about the minimum energy to dig it out as our work function, we're going to have our maximum amount of energy left over. Cool, so I think from here, like if I'm looking for my minimum frequency, that corresponds to my minimum energy, which is my work function. So maybe what I'll do from here is I'll solve for my work function. So work function is going to be equal to EK, oh, I think I did that a little bit backwards there. It's going to be our photon energy, that's a little bit better, minus EK max. So all I did was take EK max and move it to the other side. I was adding, so subtract for opposites. Nice. Now my photon energy is given to me, so I'm going to go ahead and leave that as photon energy for the time being. EK max, we've got two options for EK max now. So we've got 0.5 mv squared, but we know nothing about the speed. And we've got our new one. I don't know why I put an equal sign there. Let's get rid of that. We've got our new one, which is Q times V stop, and we do have information about our voltage, our stopping voltage. So I think that's the one that we want to deal with. So let's go ahead and plug in some numbers here. So energy of the photon, oh boy, that's way too high. 1.1312 times 10 to the negative 19 joules. And we want to subtract from that Q, we're talking about electrons, so it is 1.6 times 10 to the negative 19 coulombs, times our stopping voltage, which, where did it go there? 0.707 volts. Nice. Take a moment to plug that in your calculator. You can put it on pause if you need to. And I end up with, and I'm hoping you're getting the same things. Let's see, 5.3168. 5.3168. Just double check that. 3168, perfect, times 10 to the negative 19 joules. That is my work function. I'm not really looking for my work function, that's my minimum amount of energy, but it does correspond to my minimum frequency. So next step, I can say, well, the work function is equal to Planck's constant times that minimum frequency. You'll notice that we're in joules up here, so I want Planck's constant in joules. I can go ahead and rearrange, so F naught is equal to the work function divided by Planck's constant. So the work function, 5.3168 times 10 to the negative 19 joules divided by Planck's constant with joules. So let's see, that's 6.63 times 10 to the negative 34 joule seconds. The joules cancels with joules. We're left with the inverse of seconds, which is perfect for frequency. So maybe I'll write this out right here. We'll plug it into our calculators. And let's see, 8 0.02 times 10 to the power of, what was it there, 14 hertz. Cool, so we figured out the frequency. Nice. Oh, not just any frequency. Hold on. The minimum frequency. Cool, so all we really did here was we looked at Einstein's photoelectric effect, but with Millikan's version of our maximum kinetic energy, using that idea of stopping voltage. Now, I know what you're thinking here. We still haven't figured out how Millikan has actually verified Einstein's photoelectric effect. I mean, it's cool, it's another way to look at stuff, but haven't really figured it out quite yet. So, what do I got here? Space to work. Okay, space to work. Good. Let's just go to here. Okay. So here's where it actually comes in. We're going to have to think back to the beginning of Unit 3 to figure this one out. So Millikan did experiments with this. Millikan manipulated the frequency of the EMR that's hitting the cathode, right? So he's shown different kinds of EMR. So for example, red, then green, then violet, then UV, then whatever else. So frequency is our manipulated variable. Our responding variable, oh, I should get into this first. Way back when, you didn't have like lasers or whatever to make one very particular frequency. So he actually used an idea that we talked about last unit. He used the dispersion of light through a prism, and you know that through a prism, violet disperses more, or bends more, refracts more, I guess I should say, than red. So he breaks it apart into the rainbow, and then he just uses a device with a little tiny slit to just get pure red light. He can move that to just pure green or just pure violet. Absolutely no problem. Then what he measured was the resulting kinetic energy. Right, so our maximum kinetic energy, and he obviously did this through V-stop because we know EK max is Q times V-stop. So Q is a constant, V-stop is, well, the thing that we actually measure, but he took that one step further and looked at our, our kinetic energy. Cool. So manipulate the frequency, figure out what the stopping voltage is, and therefore the kinetic energy. Any ideas what the controlled variable needs to be? Remember, each type of metal has its very own work function, so the controlled variable needs to be the same metal surface every time. So in other words, it needs to be the same work function with the same threshold frequency. Right on. So essentially what he found was time after time after time, this graph. So we got frequency versus EK max. Now this might not look like much, but this is a very impressive graph. Very impressive graph, especially when we go and we start to extrapolate. So one note with this is a linear relationship, not a direct relationship, just goes through 0, 0, but a linear relationship. And we know how to deal with linear relationships. So here's some of the stuff that he found time after time after time. The slope was always equal to Planck's constant. Slope is always equal to h, and the magnitude of the y-intercept was always equal to the work function. Pretty neat. A little bit too convenient to be a coincidence, right? A little bit too convenient. We still haven't really verified it yet. So let's check this out. Let's go through. You recognize this, I hope. Known equations versus graph equations. So let's go through and let's have a look at this. Our graph equation. Oh, I'm skipping a step here. We should start with y is equal to mx plus b. So y is EK max. Right? So here I've got EK max right up here. That's going to be equal to slope times x, and x in this particular case is our actual frequency over here, and that's going to be equal to, excuse me, plus my y-intercept, but we understand from our graph that the y-intercept is actually a negative, so we can just kind of keep that in mind for later. So there's our graph equation. Our known equation, what we look at for this one, is, well, Einstein's equation is what we're trying to show. So Einstein's equation is the photon energy is going to be equal to the work function plus EK max. Nice. Now what we know about this is from my graph equation, I've got y is equal to everything else. So ek max is equal to everything else. I want to make my known equation look like that, so I'm going to make ek max is equal to everything else. So that's going to be my photon energy minus my work function. Oh, hey, yeah, I bet you a lot of people can start to see where this comes in. Okay, cool. Next step that I want to do is I kind of want to stack them up to make sure that they fit. And if my known equation fits my graph or my experimental equation perfectly, they should be the exact same equation, right? So let's start with our graph equation. I've got ek max. That kind of looked weird there, but ek max is equal to slope times f plus my y-intercept, which was a negative. So I might just change that to minus my y-intercept. Make it a little bit clearer later on. And then I need to stack these two things up. So obviously ek max is the same thing as ek max. Those two things are exactly the same. Slope times f. Well, I don't really have slope times f. I might need to expand this on a little bit more. I know that my photon energy is h times f. So that's pretty good. And notice we're dealing with our actual frequency. We're not dealing with our threshold frequency, but our actual frequency. So this term has f in it. This term has f. Those have to be the same term. So h times f. Cool. Those two things are exactly the same. And then minus my y-intercept. Well, my y-intercept must be my work function. Those two things must be exactly the same. So in other words, slope times f is equal to h times f. So slope is equal to Planck's constant. And the y-intercept is indeed equal to my work function, or the magnitude of my y-intercept. So we took that experimental evidence, that graph that we got over and over and over and over again. I say we like I had anything to do with this. Millikan did. Good job, Millikan. And we compare it to Einstein's equation, and it fits perfectly, which is awesome. So this graph, this is Millikan's verification of Einstein's photoelectric effect, right? In a very, very concise, very simple way. You should know, drop my felt pen, you should know this graph, absolutely know this graph, and know what this graph shows us. So all these features, it says for the diploma exam, we don't really have one of those this year, but if we did, well, you would need to know this. So again, the y-intercept, or the magnitude of the y-intercept is the work function. We haven't talked about this one yet, but our x-intercept is actually our threshold frequency, and then the slope is Planck's constant, but this is only for graphs where we have ek max versus frequency. If I were to change this even a little tiny bit, so let's say that I had v-stop versus frequency, the shape of the graph would actually be the same, but none of the important pieces like the y-intercept, the x-intercept, or the slope would be the same anymore. So keep in mind, you change one little tiny piece of this, everything's kind of out the window. Cool. So that is our lesson for today. Millikan's verification of Einstein's photoelectric effect. I hope you enjoyed it. Please make sure you're doing a little bit of practice, and let me know if you need any help with anything. Bye for now, Physics 30s.